All right, so next we will talk about the synchronization problem and the tools that provided by those language or even operating system for solving the problem. Okay. So what's the synchronization problem? Specifically, the synchronization problem we care about for shared memory programming is that if the threads or the process can run in parallel and operate on the same data concurrently, then the computing result will decided by the execution order among those processes. So in order to make sure the execution result, right, follow our programming logic, sometimes we have to synchronize or force certain execution order among processes. Okay, so that's why we have this synchronization problem. Okay, and we have here is the classic example to show why the processes need to be synchronized. Okay, especially when the process they try to operate on a concurrent access data, right? A shared data like the shared memory programming. Okay, so here, right, we have two, process, or you can say threads. Try to operate on the variable or the memory content called the counter, right? So one process called the counter plus plus, the other code the other codes counter minus minus. So as a programmer, what you expect should be, right, if I know -1 and then +1, the result should remain the same. However, it will not be the case from our operating system or computer system. Okay, because the statement we see from the programming language is not a single instruction, right? It may not be a single instruction. For example, here, plus plus and minus minus, they actually consist of 3 instructions, right? So this statement is actually contain 3 instructions. Okay, so for our operating system, it only execute the code at the instruction level. And the operating system will always try to context switch between the processes or threads, right? For fairness issue or to provide, because there are time sharing machines, right? So what happened is that if we have the context switch happens in between those instructions, then maybe the memory state is still unstable. It's only modified by in the register, but haven't been written back to the memory. So as a result, as we shown over here, right? If we execute the first 2 instructions from plus plus first, and then context switch to minus minus statement, and then switch back to the last instruction from plus plus, then you will actually override or ignore the result, right, stored in the register by minus minus and change the value to 6. And the last instruction come from the minus minus, it will override the memory content again by its own register value, right? By its own value in the register. Okay. So at the end, although we code those 2 statements at once a piece, but the result should be 5. But at the result, you can see it's only 4. Okay, so of course, if you change the order, you will find the result maybe 6 also. But actually, there's only one correct result. That should be 5, right? Neither 4 or 6 are correct. Okay, so that's why that means we need to control the order, right? At least we need to make sure the plus plus instruction for plus plus or minus minus, they can be executed, at once, right, without interleaving. Okay. So how can we control the execution order? Okay. So the first way to control the order is what we call the critical section problem, right? So inside the critical section is just a piece of code in our program, okay? And the definition of a critical section is that inside this section of code, there should be only one process execute the code at the time. So that means there shouldn't be any interleaving behavior, right, in this section. So you can avoid the problem we solve, okay? So the most important property of a critical section is what we call the mutual exclusion, right? Ensure only one process in the critical section at a time, okay? And of course, how can we ensure mutual exclusion is that we need to write some synchronization code, right, before and after the critical section. So it can allow us to protect the code inside the critical section. Okay? And of course, there are many ways to write the entry section and the exit section to enforce mutual exclusion. And the easiest way is to use lock, right? Because the lock can only be handled or processed by a single process. So the first process enter the critical section can obtain the lock and keep the lock, while rest of the process will not be able to enter the critical section without acquiring the lock. So other process need to wait until the process exit the critical section and release the lock. So that's, we can see, is one of the easiest way to implement a correct solution of a critical section. Okay? But however, if you took the operating system course or if you study the implementation of a lock, you will find that a simple implementation like what we show here may not be a very good implementation because it may consume is what we call the busy waiting lock because we have a while loop, right? So even so, the process cannot enter into the critical section. It still need to execute the while loop, right, and burn our CPU cycle. So it may not be something we want. Okay. So of course there are more efficient way or better way to implement those lock mechanism. And the pthread library or many thread library will implement the lock for us, right, and provide the lock as an API for the programmer to solve the synchronization problem. And for pthread specifically, the lock it provides is called the mutex. It's an abbreviation of mutual exclusion, right? So it's basically a lock for mutual exclusion, right? So the API to operate a lock is quite simple, as you can see over here. First of all, the lock mutex is a predefined data type. So you have to create the lock by declare the lock. Okay. And the lock is actually not just a Boolean point variable. It's actually a data structure. It's a class. So you have to initialize the lock. So that's why we need to call the mutex init before we use the lock. Okay. And of course, that's why we need to call the mutex destroy, right, to release the resource associated with the lock when we don't need to use the lock anymore. Okay, and in between, you can use lock and unlock to repeatedly reuse the lock in your program. And of course, the correct implementation will be you code the lock before you enter the critical section and code unlock after you leave the critical section. And if you don't implement in this pattern, actually it will cause some problem, because if no one free the lock, then no one else can enter the critical section. Then your program may hang in there, or even cause or create a problem, what we call the deadlock, right? Although the API is provided for the programmer to easily operate on the lock, but still how to use the lock to protect the critical section is up to the user. So that's why still, as a programmer, you need to know the logic of solving a synchronization problem. Okay? The lock itself doesn't solve the problem for you. It's just a tool. Okay? All right. So we will use some classic synchronization problem to see how the lock could be used. And one of the classic problems is called the bounded buffer problem, right? And the problem is from when you have two processes, one called the producer, the other called the consumer. They share a buffer, a shared memory, right? It's a buffer to pass the data from the producer to the consumer. Okay, and it needs synchronization because this buffer is a bounded buffer. It only has a limited number of space. Okay, so you cannot just keep writing data to the buffer or keep reading data from the buffer. Okay, you have to synchronize the producer and the consumer, so you will not allow the buffer to be overflowed. Okay. The one way, right, to implement this solution correctly is through the by checking the or compare the pointer. You write the data to the buffer and you read the data out of the buffer. Right, it's what we call the in and out pointer. Okay. And if the position of in and out are the same, then we can say we can identify the buffer is empty. And of course, when the buffer is empty, that means the consumer should not keep reading the data. Okay? You need to stop. Okay. On the other hand, if in plus one equal to out, then that means we use this condition to identify the buffer is full. Okay, so when the buffer is full, then of course the producer should not keep writing the data anymore, okay? Because it will overwrite the data that haven't read out by the consumer. Okay, so it's a way to synchronize between the producer and consumer. However, this strategy, as you can see, you will not be able to fully utilize all the space or entry of the buffer, because if you allow the producer to keep writing until the buffer is actually full, then you will reach the same condition for empty and full, right? Because the pointer position for in and out will be the same. So in that case, you will not be able to distinguish between whether the buffer is full or empty. So this strategy, the condition for full, actually is the case when you still have one empty entry left in the buffer. So it's a way to coordinate or to synchronize the two processes without using lock, but it will waste resource. Okay. So this solution is not necessarily bad, because coding lock usually associated with more overhead, right? It's a more complex operation. But if your memory space is scarce, all right, you want to fully utilize your resources, then using lock will be a more efficient solution. And also using lock will be easier to implement the code, right? And here is the pseudo code for what I just described. If we just use the pointer precision to identify whether the buffer is full, like we're showing above, or whether the buffer is empty, like showing below. Okay, and so we use this condition to check, right, to synchronize between the two processes, so they can communicate, or they can collaborate with each other correctly. Okay, right. But if we use lock, will be much easier, because all we need to do is that to provide, right, the critical section. If we use lock, then we can solve the problem with the concept of critical section. And the concept of critical section is quite simple and clear, right? That is, we need to identify what are the shared data among processes or threads, right? And to put that code in the critical section, so we can ensure this memory content cannot be accessed concurrently by both the producer and the consumer. And then we won't run into those what we call the race condition, or the data concurrent write problem. Okay. So as you can see, for producer and consumer, we can use a counter to count how many items are written in the buffer, right? And if the counter equal to the buffer size, then obviously that means the buffer is full. And while if the counter is 0, then obviously that means the buffer is empty, right? So we can use the value of the counter as the condition to distinguish whether the buffer is full or empty. And so the producer and consumer can, right, keep reading and writing in the correct way. Okay. However, the counter, because it has to, right, operate by both consumer and producer, so the counter itself become the code that need to be protected in the critical section. So we will code the lock and unlock, right, before we operate on the counter. Okay. All right. So pretty much it. So for your homework, you will certainly run into some of those issues when you need to have multiple threads operate on the shared memory variable. In that case, just remember to use the lock to protect those operations. Okay. All right. And the next is so synchronization. There are many, actually, there are many reasons for the programmer to synchronize between threads and the processes. To resolve the concurrent data access problem is one of it. Okay. And another situation or use case is that the process, between process, they need to have, they need to trigger their operation, or they need to synchronize their execution order according to some condition. Okay. For example, maybe one thread is responsible for reading the data out from the file, and another thread will take over the data written in the memory and start doing the processing. So we need to have a condition to indicate when we can start process the data in the memory, right? And so so many synchronization is based on condition. Okay, so that's why we have this condition variable as another tool for programmer to synchronize between the threads according to their behavior of their threads or processes. Okay, so the condition variable, again, very much like the mutex lock, right? It's only it's a variable, it's a token. Okay, represent a condition, and the API for condition variable are the ones that try to operate on the condition variable, right? And so basically, usually we have those three API associated with the condition variables. The first one is wait. So the wait means that whenever a thread's code is wait, then the thread will be blocked, okay, until another thread's call the signal on the same condition variable. So you can see that the signal means right, the basically indicate that the condition occurs, okay, and the threads waiting on the condition can be wake up by the signal, okay. And finally, signal can only wake up one thread at a time. So we also have the broadcast to wake up all the threads associated with condition variable at once. Okay, so you can either wake up one at a time or all at once. Okay. All right. So again, similar to the mutex, condition variable is a special type, right? And so you have to declare the variable and initialize the variable before you use it with the API we just mentioned. Okay? And also noted that for pthread library, the conditional wait API require two arguments. One is the token or the handler of that condition variable. The other is a lock, a mutex lock. The mutex lock we just introduced. And we will explain why it required this lock as well. Okay. So first of all, how we use conditional wait, as you can, and the conditional signal, you can see that those API needs to be called within a critical section. Okay. And of course, we know a critical section is protected by a mutex lock. So that's why for the conditional wait, the mutex lock it required should be and must be the mutex lock for the critical section. Okay. So why do we need this the lock, right? Especially we need to pass the lock to the conditional wait code. Okay. The reason is that you will see that for critical section, as we mentioned, supposedly, right, it should only allow one process to running inside the critical section at once. Okay, so if one process, imagine here, right, if one thread's call action, right, and the condition haven't been occurred, so this thread will be blocked inside the critical section. So that means, by default, that means it hasn't released the lock yet. So if it doesn't release the lock, then that means no one else can enter the critical section or call the conditional signal. As a result, you will have a deadlock situation, right? Because the thread calling action is waiting for the thread calling counter. But the thread calling counter is waiting the lock hold by the threads calling the action, right? The action call. So they wait each other. Then, of course, that seems like a wrong implementation. Okay. So why it doesn't occur, right? Is because when we code conditional wait, at the end of before this code, put the thread to sleep, he will release the lock for us. Okay, and so it needs to know which lock to release, right? That's why the mutex lock need to be passed to the conditional wait function. So the function can release the lock for the programmer or for that thread. And the thread can release the lock because the thread will be put to sleep afterwards, right? So even thought is still within the critical section, the thread is sleeping. So that means we should be able to allow another thread to enter into the critical section. Okay. So that's why after the conditional wait is called, the mutex lock will be released. So any other threads can who code the counter can enter the mutex lock, can enter the critical section, and he can eventually code the conditional signal when the condition when the condition is occurred, such as x equal to 0 in this sample code here. Okay. All right, and however, after the signal is called, as we mentioned, supposedly it will wake up the sleeping threads, right? However, remember the threads that put to sleep, you already released the lock for the critical section. So even so it's waking up, but it still cannot run, it still cannot return from the conditional wait function, because the last code in the conditional wait is to reacquire the lock. Okay, so the thread is wakened can still block inside the conditional wait until the counter threads call the mutex unlock and release the lock and exit the critical section. Then the action thread can truly break out or return from the conditional wait and continue the statement in the critical section. Okay, so basically at the end, you will find that the implementation showing here will allow those threads coordinate between, synchronize between each other correctly according to the condition signal, and they also follow the mutual exclusion requirement for the critical section. Okay. All right, so that's basically already so this slide is what I just told you about, and you can follow, you can summarize all those again. Basically, you have to put in the critical section, because we have to protect, make sure usually the variable that determine the condition, such as x over here, needs to be in the critical section, right? Otherwise, because the condition is the x variable is accessed by both threads. So according to the to avoid race condition, we have to put the x into inside a critical section. And we also need a critical section to ensure that when the thread is wake up, his state is the same when the signal is called. Okay, so that's why the whole thing has to be inside the critical section. Okay. All right, and here's just a step by step as what I mentioned. What truly happened is, you can see after the action thread is blocked in the conditional wait, it will actually release the lock and put himself to sleep. So it can allow another threads to enter the critical section, right? And be able to call the signal and wake up the sleeping threads. But even the thread is waking up, he cannot return from the code, because he has to reacquire the lock again. So basically, it still has to wait until the other threads exit the critical section. So the mutual exclusion can still be enforced between those threads. Okay. All right. So however, this is the API, right, defined and provided by the pthread library. For other thread library, you might not find exactly the same interface, right? So some of them doesn't require you to say put it in a critical section or pass in the lock of your critical section, right? They may provide or implement or define the API for conditional wait in a different way. Okay, but for pthreads, that's what happened. Okay, and that's what we need to follow in order to make sure we interact with the pthread library correctly. Okay, all right. Okay. So after we explain the condition variable and mutex lock, then most of the time we have to combine both tools together to implement some, to solve some synchronization problem that's more complex. Okay, and one of the use case is thread pool. Okay, so some of you probably already know what's a thread pool. So thread pool basically is a technique that we create the threads in advance, and we create a fixed amount of threads and put them in a thread pool. So we can reuse those threads to use them to execute different function during our in our program. So we don't need to recreate the threads repeatedly, because thread creation is still it still takes time. So sometimes we want to use a thread pool to avoid recreating those threads. Another reason is that if we allow the program to just arbitrarily create threads when they need it, then you cannot bound the number of threads in our system, and you might consume too much resources, right? And so, for example, we only have limited memory, limited CPU core, limited network port, right? So if you create too many threads, you may not have enough resource. So if we use the thread pool technique, then we can always bound the per reason or the amount of resources we need for our thread program. Okay, so especially for network server, usually it is manage the connection by those threads in the thread pool. Okay. Okay. So how can we implement thread pool? Of course, again, some of the language have library directly provide the solution for thread pool. So you can even directly code those high-level API to create thread pool and utilize a thread pool. But here, at least for pthreads, its own API doesn't have that. Okay, so you might have to implement it by yourself if you want, by using just the condition variable and the mutex lock we mentioned. Okay, and the basic idea to implement a thread pool is that the thread pool is actually a queue. Okay, a queue of threads that created in the pool, right? And those threads, as we will show later, they are implemented as a infinite for loop that try to fetch the task, okay, from a task queue. And each task is represented by a function pointer. Okay, so the thread can pull any task from the queue and call the function pointer to perform the execution. And so after you finish that function code, you will try to pull another task from the task queue. And so it can repeating the thread can be reused to execute multiple tasks. Okay. So as you can see over here, a task can be defined as a pointer with the argument, just like the pthread create API, right? And this task will actually be stored in a task queue. Okay, and we will create a pool of threads that try to fetch the task from the queue. So this is how the thread pool will function. Okay, and of course we have some other pointer for the threads to manage or to in-queue or dequeue tasks from the queue. Okay, and also we will have a lock and condition variable that is needed to coordinate the threads when they try to dequeue a task from the queue, because the queue is a shared memory content among the threads. So when we try to dequeue or enqueue, we need to use the lock and condition variable to do the synchronization. All right. Okay. So here we can see the detail of the implementation, and basically you can see this is the thread function, okay, for a thread. Okay, so when the thread create, we will ask it to run this function. Okay, and this function is basic, as we mentioned, it's an infinite for loop, and try to pull the task and operate the thread pool data structure. Okay, and of course, as we can imagine, first of all, we need to have a lock, right? So basically, first of all, we need to make sure only one thread can call the dequeue function at a time. Okay, and however, if the queue is empty, right? Then we have one way is use busy waiting technique, right? We can have a while loop and try to pull the task from the pool, right? If the task is 0, then we have to try to pull the task again. But this is if we keep while loop on this pulling event, then it will burn our CPU cycle, right? So more efficient way to implement it is use the conditional wait. So if the pool is the task queue is empty, then we can simply put the thread to sleep, right? And the thread can be wake up by another thread that try to create a task or in-queue a task to the queue. Okay, so in that way, the waiting thread will not burn our CPU cycle. So this implementation using conditional wait will be a better implementation. Okay. And of course, as we just explained, if you use conditional wait, you need to inside a critical section. And so we have a mutex lock to protect our critical section and protect our condition variable. Okay. All right. And of course, you can imagine the thread will be blocked over here until it is able to actually retrieve or dequeue a task from the task queue. And after you dequeue the task, right? This is how we dequeue it, and we will call the function. Okay. But as you can see, the critical section is actually only ends after we do the dequeue actions. So after we copy or move the task from the queue to his local variable, then we can exit the critical section. Because execute this task could be time consuming. And since the task will only execute by one thread at a time, so we could assume the task execution itself doesn't need to be inside the critical section, because it won't be accessed by multiple threads. Okay? Of course, that's the assumption. That's the case. If the task doesn't involve the execution of the task itself, doesn't involve any race condition. If it does, then unfortunately, you need to put the task execution in another critical section as well. Okay. All right. But basically, this is how we can implement a thread pool. So the thread can just run in parallel and fetch the task from the queue independently and only synchronize when they have to operate on the queue itself. Okay. All right. Okay. So so next we will briefly introduce semaphore, and the semaphore is again another way to solve a certain type of a synchronization problem, the type of problem that depends on uh, the limited unit of the resource. Okay, so for example, if you have only 10 network port can be used, so then you need to make sure, right? You cannot create, or you cannot allow the threads to, you can only use at most 10, right? So the resource is need to be counted. Okay. So the semaphore itself is a record of how many units of a particular resource. The resource can be abstract, to be a network port, can be a file, can be anything. Okay. And the counter, we will initialize it to some value, and that value only usually means the limit of the unit. Okay, so if the record is set it to 1, then that means you only allow one thread or process to use the thread to use the resource at the time. So then this is basically the same as a mutual exclusion, right? So if the record is 1, then it means we also call it as a binary semaphore. And the binary semaphore is the same as mutex lock. Okay? So normally we use semaphore because we have multiple unit of resources. And so the semaphore should be, in that case, we call the semaphore as a counting semaphore. And the semaphore, again, can operate only by 2 operations, wait and signal. And very much like the condition variable, the name is the same, but the behavior is a little bit different because the signal and wait over here is try to do the counting. So as you can see, the implementation signal try to increase the count by 1, while waiting try to decrease the count by 1. And the wait code will block the threads when the resource is less than 0. Okay, so when the resource is if you don't have any resource left, then the wait function will block the threads, okay, to avoid you overuse the resource. Okay? While condition variable, if you remember, it's more like operation on a queue. So the signal for condition variable is it's an action of dequeue, while wait is an action of enqueue. And so the dequeue act you dequeue to wake up some threads that was block enqueue, called the enqueue. So basically the queue will never be right empty, right? It will be it will be either empty or there's something over there. It's not a like counter, okay? But semaphore is a counter, okay? So the behavior will be a little bit different, okay? The way to use semaphore, again, like before, you have to declare it, initialize it, destroy it, and the wait and post equal to signal, what we mentioned. And in addition, usually at least the semaphore implemented by the proxy, by the OS, is you also have get value. So you can query the value of the semaphore. So sometimes you can avoid to call wait if you find that the value is already 0 and you don't want to be blocked. So you code get value to pre-check the value. Okay. All right. As you can imagine, if you have limited resources, then in that case, you probably using semaphore will be the easiest way to synchronize your processes or threads. Okay, and also remember, at least for the semaphore, the API we introduced here, you can see it's provided by the operating system. So in fact, unlike the mutex lock, can only be used by pthread and within the thread, for the thread within the process. The semaphore can actually be used across processes. Okay, so it's different from mutex lock. Okay, or the conditional weight, condition variable we introduced, that is provided by pthread library. Okay? And but however, the then thing is again, semaphore is only a tool, so it's up to the user how to decide when to call wait, signal, and all those things. Still, the programmer need to use the tool properly. Okay, let's just spend 3 more minutes and to wrap up the last tool. Okay, so the last tool is monitor. Okay, so you try to resolve the problem. We seen previously that it's up to the programmer to decide how to use the API. Okay, so the monitor is a special class provided by the language. Okay, and you will find that it's similar to the OO class, right? The class for the OO language, except that the method defined by the class, by default, they can only execute one at a time. Okay, basically, you can imagine that means you have a mutual exclusion between the method of a class. Okay, the synchronization is built into this language, built into this class, and the programmer doesn't need to control, right, when to call lock and unlock, etc. Okay, okay. So that's the idea of a monitor, and you can see that, for example, in Java. Okay, so for Java, it implement or provide a monitor as a special class, and it provided in a more flexible way that, as you can see over here, for the method of a class, you can predefine this synchronize keyword in front of your method. And if you have this keyword, then the Java knows that the method with synchronized keyword cannot be executed at the same time. Okay, so it's a more general, more flexible monitor model, because that means you could have some method without the keyword. Then for those methods, it still can be concurrent executed by multiple threads. So it's all up to the user to decide whether the function can be, must be run in a critical section. Okay? And finally, for Java, they not only provide a monitor, of course, he also provide the mutex lock. And the way he provided is also at more language level. As you see over here, it's you use the synchronize keyword for variable, and then what happened is the Java, when it do the compile, he will analyze your memory reference, and if you have any statement that try to access this variable, then he will automatically generate the lock and unlock between between this statement. Okay, so you don't need to code lock and unlock by yourself. The compiler can identify itself and generate the code for you. Okay, And because the locking mechanism is at the statement level, so sometimes we also call it a fine-grained locking mechanism. While previously, the monitor is a more coarse-grained, right, synchronization technique. Okay? All right, so we briefly introduced those tools, and for our homework, it's not that complicated. So usually it should be quite straightforward, and for you to figure out which tool you use and how to use it. And also, we have so many tools. The important thing is each type of tool, right, is designed for a specific certain synchronization problem. So you should first identify what kind of synchronization problem you try to solve, and then pick the right tool so you can more easily implement your solution. Okay. So although the monitor is at a higher level, is more powerful, but doesn't mean that you should always rely on the monitor to solve your problem. Okay. All right. So that's it for the pthread chapter. And for the next lecture, we will continue to introduce the compiler generated thread programming. Okay. All right. So if you have any question, you can feel free to ask now. Okay.